Hello and welcome. Today, we are actually going to be training a PyTorch model in order to convert a handwritten digit into an actual keystroke. So, last time we covered the dataset creation fundamentals, which will allow us to load the image label pairs into our PyTorch training process by defining a custom dataset class and then using the PyTorch Dataloader class to load the data into the model. So today we're actually going to be doing the model training, and that requires knowing a few key concepts and understanding the training loop. So let's get into it. Okay, so last time we loaded up our data loaders with data so we could give it to the model for training. We checked to make sure that that was all kosher, so that the data loader was providing the right image and label. So in this case we got 5 and the label's 5. Looks great. So now we're going to make a model from scratch, and I'd suggest you look up a few key terms, but we're going to start off with this layer process. So there are kind of 3 categories of layers that you can have in these models, and the first is the input layer, and that's just going to be your image. And you're going to feed the image like numbers into these hidden layers, which are going to calculate some math stuff, which is the model architecture and weights here, and the outputs to an output layer, which are going to be our predictions. So we can talk about fully connected layers, which are what we're going to be using, but that would take too long, so look that up. Similarly with activation functions, this is just going to enable the math to be performed so our model will learn. And then we're going to go ahead and define the model architecture here. We're going to make a class called black and white model, whose parent class is this torch NN module, which is just the model class that PyTorch uses. And we're going to make sure that we define the number of classes as 10, because that's what we want. That's our output layer. Our input is going to be 28 by 28. And we're using a series of layers with 64 nodes in them. That's just going to be passed through a few times, and we're using this ReLU activation function on each of these layers before we finally get the output value here, x, which is going to be a vector of 10 values for each image coming out of the model. And we call this forward because it's a forward pass. So we initialize the model with random weights after we actually run our model class and define it. And then we run an example image through this untrained model. So hypothetically, we should be getting a random output for this sort of thing because the model's not trained yet. We just initialized it at random with no weights to speak of. Well, not no weights, but just random values for weights that hasn't been optimized. We get a tensor out here for this image, and the largest number is going to be what the model thinks the handwritten digit is, and in this case it seems like the largest value is going to be 1.3, which is a 9. We can apply a softmax in order to get a probability on that. So it's got 26 probability of being a 9. And 23% probability of being a 0, 1, 2, 3, 5. We can return a predicted class 2 different ways. And both end up with the same thing. So we get a predicted class of 9. Now that we have the model trained, now that we have the model defined, let us train the model. We'll start with this training loop concept, and this is an important one to understand. You have the data coming in with the true labels into the model. Then you have the model giving a prediction of the labels for each image, and the loss is calculated for that. Now the loss is going to be the difference between the predictions and the truth. This loss allows the model to tweak itself, to do some corrections with backpropagation, update its parameters and weights so that hopefully on the next iteration it's going to do better. And on the next batch you get more data with true labels, that model makes some more predictions and calculates the loss, updates itself, and continues doing that for each batch. We define the criterion here as being cross-entropy loss. That's the loss function that we're going to be using to train this model with, and cross-entropy is a good starting point for basic classifiers. Similarly, you can use the atom optimizer in order to help tweak the model weights. We feed it the network's parameters and give it a learning rate. Now there's other arguments you can put in here, but these are the basic ones that you will absolutely need. And learning rates can make or break a model. Basically, if you have the wrong learning rate, the model may not train. So a good rule of thumb is starting off with a learning rate of 1 times 10 to the minus 4 or minus 5. Now let's just train on this training data, and we're going to do 10 epochs. That means 10 passes through the data set. So for each epoch, we're going to iterate on the training data loader, which means that we are going to load consecutive batches in the training data loader. And remember, we assigned 10 image label pairs per batch here. So for this batch of 10, we're going to get a list of input images and labels. We zero the optimizer gradient so it doesn't remember the jump from last iteration. And then the basic way you get the inferences out of the model here is you just use the model here, you put the images into the model, and then you get the output labels. Once we have these outputs, we can put it into this loss function criterion because these are the outputs from the model, and these are the true labels, or what they should be. And with that, we can calculate the loss. Then we do a backwards pass on that loss, and we take a step on the optimizer, and that updates our weights. So hopefully on the next pass, the model will perform better. Here we're just printing some loss values to make sure that our training is proceeding as planned. We want the loss to decrease over time. Let's take a look. We start off with a loss of 1.6, which is really quite high, but you can see immediately that it decreases and keeps decreasing on each consecutive pass until it reaches 10 epochs, and then it's finished training. And we could have gone longer, but we're going to see what happens when we add in the validation data as well. So now that we have a somewhat trained model here, we can put it into eval mode, which prevents further calculations going in and changing our model. And then we have an image input here. We feed that image to the network to get an output where we can print the logits, but we can also get the predicted class out by using argmax. So here are the raw logits, and the largest logit is going to be in class 5, and that's the predicted class. We can have some basketball analogies to better understand some of these terms, but I'm not going to go into that because that'd take too long. So moving on to the training loop, we are going to be doing 5 epochs here, starting off with infinite number for the minimum validation loss so that it will keep track of the minimum validation loss for each model each time the batches are going through here so that we can kind of determine whether we should save the model or not. If the model is overtraining or just memorizing the training data set, we can know this by using the validation loss. If the validation loss stops going down, that means that the model is no longer training effectively. It's overtraining, which means that it is just memorizing the training data set, which doesn't make it generalizable to other data sets. So we don't want that to happen. That's why we use the validation data set, which is what we use in this section down in here. And we keep track of that validation loss so that we can tell when to save the model to a file. And we're saving the model to bw modelweights.pth. we give that a try, and we'll be able to see the loss values for the training set and the validation set. And the validation loss has gone down compared to infinity in the first part, so it saved the model. And it also decreased from the previous pass, so it saved the model again. But after that, then the loss no longer decreases. So we know that training is over. The model is just overtraining at that point. Now we can run the trained model on a test image. Loading the test data, we see that there's 28,000 data points, and they do not have labels associated with them. So we can't really do metrics, but we can just do inference. And I guess if you wanted to participate in the Kaggle competition, this is the data set that you would be predicting on. So we'll grab one image from this set and we'll take a look at it. Looks like a 2 to me. We'll convert it into a batch float tensor so we can load it into the model appropriately. We're loading our model here, the architecture, and then we are using our saved model, loading it in with torch.load and using the load state dict in order to load those model weights into our model architecture. You can save both the architecture and the weights together into a single file. But this way we have the original definition of the model, which is easier to look at, and we can have smaller weights files. And we can put this into eval mode and make sure you use torch nograd so that your computations are more efficient, and apply the argmax to get the predicted class out. And the predicted class is 2 from our trained model, which matches this handwritten digit. So there you go. We have success. We have a trained model we can use for any sort of downstream handwritten digits tasks, and we know how to load the data into here and get what we need out of it. It's all good.